Hello, friends. This lecture will take an overview of ancient Indian mathematics, and will talk about the contributions of ancient Indian mathematicians to the area of mathematics. This is a part of the lecture series on Indian knowledge systems in general, wherein we shall introduce you to the various branches of knowledge that existed and developed in the olden times in India. This is a lecture on mathematics by the Department of Mathematics of Bitco College, Nasik Road, and I sincerely thank Professor Borse and Professor Divti of the Department of Mathematics of this college for helping me to create this presentation and this lecture by providing the necessary material and the required guidance. To begin with, um, uh, mathematics is one of the branches that developed in India, and there are several facets of knowledge that existed and that grew uh, as the civilization developed in India. So the uh, the branches of knowledge um, uh, that advanced in the course of time in the ancient times in mathematics can be found in the scriptures such as Vedas and Upanishads and some other scriptures, some other granthas as we call them. And there are Vedas, and then there are some Upavedas of those Vedas such as Dhanurved, then Ayurved, Sthapatya Ved, there is Gandharva Ved. So each of these explains, or each of these uh, explores the ideas related to that field. For example, Ayurveda, as many of us may know, is in practice in the today's world, and is a science of medicine. Uh, Dhanurved was at that time the science of archery and weaponry in general, and also the science of warfare. Sthapatya Ved was the science of architecture and design, and Gandharva Ved was the science of music and art and dance in general. These are the branches of knowledge that flourished in India at that time, and mathematics is one of those branches. Um, so the purpose of this whole lecture series, and especially the purpose of this presentation, is to introduce the students to the advancements of mathematics that took place in India at that time, and to make them aware that Indian scholars were capable of thinking of very advanced ideas about mathematics. How mathematics originated, how the ideas in mathematics originated, and how they developed is something that we shall discuss in this presentation, and who were the prominent figures in the development of mathematics. Um, Initially, mathematics began uh, uh, when people started counting objects. When they started counting objects, they needed numbers, and that is how mathematics began. That is the germ of mathematics. Um, as um, things went ahead, they not only counted objects, but they also exchanged objects and they exchanged commodities, and with that the idea of trade emerged. And then they also started earning profits, they also started having losses, and they also started lending monies to each other. So thereby giving rise to the idea of debt or loan. And that's how the with the transaction of money, the idea of mathematical operations or arithmetic operations evolved through the times. So it was the idea of counting, and then subsequently the idea of trade or the uh, practice of trade that um, made mathematics to develop. In not only in India, here we are talking about India and in the Indian context, but in general over the world, in any civilization, you can uh, trace back the origin of mathematics uh, in the idea of counting, and in the origin of trade. Also, as the vision of the human being expanded, and when he started observing the nature around, he also first of all his attention was attracted toward the celestial bodies, that means the stars and the planets. And um, he was astonished by the movements and the motion of those bodies, and therefore that drove him to observe those motion carefully, and to come to some conclusions about the motion of those bodies, which also and he realized that though the motion of those celestial bodies were governed by some mathematical laws, and he was further induced to find out those motion of uh, those the laws of mathematical laws that govern the motion of these celestial bodies, which gave rise to the study of astronomy. And mathematics also developed as a tool to study astronomy. Also, in ancient India, it was a very usual practice to perform penances. So, penances meaning, as we call them, yajnas or havan, and to construct yajna kunda or havana kunda, or as we call it in English as altars. They needed some knowledge of geometry, because these altars or these havana kundas were geometric in nature, and therefore uh, to know how to construct them in the desirable fashion, they needed to know the relationships between the parameters of those geometrical objects. Therefore, even they they were induced further to study the relationships between the parameters of the geometrical objects, such as if you consider a circular Havanakunda, then how the diameter and the periphery are related to each other. So, if diameter and the circumference are the two parameters, then how are they related to each other? If diameter and area are considered as two parameters of the circular Havanakunda, then how are they related to each other? Or if square Havanakunda is to be built, then how is the side of a square is related to its area? So side and area are the parameters, and what is the relationship between these parameters is something that they studied, and they came to some definite conclusions about these. And even here we can clearly see the study of mathematics that was carried out by those scholars. So it is in various contexts that they studied mathematics. First of all, initially in the prim- primitive ages, they needed mathematics for counting objects. Then as uh, they began to trade, they needed mathematics to keep the account, or the for bookkeeping, as we might call it, to keep the record of profit and loss and date and loans. And probably also in the later times we see that interests uh, were also incurred, and therefore so some sort of banking was done over there. So that was the commerce and trade that came into picture, which also contributed to development of mathematics. Then came astronomy, uh, which for which they needed some really good sophisticated mathematics in order to study the motion, or the motion of the celestial bodies in the space. And also they studied the geometry for constructing um, the Havana kundas or the Yajna kundas or the altars for um, conducting penances. So that is the beginning of mathematics in India, and how it evolved over time. So the here we see one uh, very remarkable invention in the ancient times in India, which was uh, very specific to India, and nobody at that time, no contemporary civilization used this idea, which is the idea of the zero. In majority of the ancient civilization, the idea of zero existed, but nobody used it as a number or as a digit. And uh, nobody, I mean, in no civilization you can see that zero was used as a number, and the number system was constructed uh, with uh, by taking zero, by treating zero as a number. um, so zero, which is shunya as it is called in Sanskrit, uh, uh, is an idea which means nothing, or uh, empty or void. And Indian scholars knew that anything when added to zero gives us that thing again. Any number, for example, added to zero gives that number back, or when we subtract zero from any number we get that number back, and any number when taken away from the number itself gives us zero. These ideas exist more or less in every civilization, but what is very specific about India is that they used zero as a number, and they constructed decimal system. So to just to um, distinguish, or to um, contrast the numbers decimal number system that Indians use from the Roman number system, uh, observe that in Roman number system, 1 is written as one vertical small segment, 2 is written as two vertical small segments uh, placed side by side. Then 3 is written as three vertical segments, and 4, 5. 10 is written as x. 9 is written as one vertical small segment written on the left side of x, that is 10, and 11 is written as one small vertical line segment written to the right side of earth. So, and this continues. So for every number they invented one new symbol. For 50 they write L, and for 100 they'll write C. And so for every new number they write, they invented new symbol, and in this way they wrote the whole number system. Whereas in India, we have only, I mean, Indians had only 10 symbols, that is from 0 to 9, that which we call as digits. And for when we write 10, we don't uh, invent a new symbol for 10. We use only the digits that are already available to us, and we write one uh, we write 0 after 1, and that gives us um, 10, and then 11. And with these 10 symbols we can write any number. So that gives rise to decimal system. And with so one advantage that we have is that we do not need more than 10 symbols to write uh, numbers. And secondly, since this decimal system has a very peculiar property that every uh, place has a value. That means the first place, the rightmost place, is called units place. The second right place is called tens place, and the third right place is called the hundreds place, etc. We can very easily add two numbers, subtract two numbers, and similarly multiply and divide numbers. So the arithmetic uh, using decimal systems becomes very easy and practically possible, which is not the case with the Roman number system. So this concept of zero is a gift given to the world by the Indian scholars. And the first person who is believed to invent this zero, and who is believed to use zero as a number is Aryabhatta, about whom we shall see in a moment, in more detail in a moment. So this is you can see the picture of Aryabhatta on the left hand side. Aryabhatta was probably the most prolific mathematician of his time. So one of the oldest and the most prolific mathematicians, and he used zero in the number system. He was a mathematician as well as an astronomer, and it is worth mentioning over here that mathematics in Indian context, the sophisticated and complex mathematics, has always developed, or has always rather developed by mathematicians as an instrument to study astronomy. So majority of the mathematicians in India were basically astronomers, and they developed mathematical techniques to study, to further their astronomical studies. Uh, so Aryabhatta was also basically primarily an astronomer who also was a mathematician, and but uh, nonetheless, I mean, even though he was an astronomer, his mathematical contributions are not negligible. They are in fact very profound in a way. So he is supposed to have invented zero and used zero as a number, um, and uh, followed by Aryabhatta was Brahmagupta, who also used zero in his calculations. And he used zero. Although Aryabhatta invented and used zero in calculations, it was Brahmagupta who used it profusely in his calculations, and he demonstrated how powerful this tool of using zero as a number in the decimal system is. uh, here Brahmagupta also is has used the idea of negative numbers, and that was the probably not the first time, but very prominently he used the ideas of negative numbers, and he called them as debts. So in Sanskrit, positive numbers are called as dhana sankhya. Dhana means possessions, and negative numbers are called as rina sankhya, and rina means debt. That means something that you owe to somebody else. So when you possess something, you are not in debt, you have it, so therefore your possessions are, your belongings are in positive. So, and when you owe something to somebody else, your possessions are in negative, so that means you are supposed to give something to somebody else, so something will be deducted from your pocket sometime in the future, so that is rina, that means negative. This slide shows the digits that are used for writing numbers, and look at the pronunciations of the digits in Sanskrit. They resemble quite with the pronunciations that we have in either Marathi or even majority of Indian languages. For example, here we have, I mean, shunya, and the pronunciations in Sanskrit are shunya, eka, dvau, tirah, chatvarah, pancha, shata. This S is to be pronounced as sh, and this is sapta, wherein this S is to be pronounced as sa. So shat is saha, as we call it in Marathi. Sapta is sat, ashta. Again here S is to be pronounced as sh, which is 8, and nava, which is now. So these are the digits in Sanskrit and their pronunciations. As we mentioned earlier, that negative numbers are called as rina sankhya, and rina means date, and the symbol for negative numbers in the ancient times was this was the symbol, as you can see over here. A dot was put on the top of the number to show that the number was negative, whereas nowadays we use the negative symbol, we show the negative number by putting a dash symbol on the left side of the number. Now, more particularly, the mathematics in the Indus Valley civilization. The Indus Valley civilization is the civilization. So there were a few sites that were excavated in the British era, and they were found by a British archaeologist, and the excavation sites were at Hadappa, and also at Mohenjo-daro, and also at Dholvira, which is in Dholvira is in, I think, Rajasthan in India, but whereas Hadappa and Mohenjo-daro are in Pakistan nowadays. At that time it was India as a whole. This civilization is about 5,000 years old, and it flourished between 3,300 before Christ to 1,700 before Christ, and its peak was between 2600 and 1900 BC. It was very sort of very urbanized civilization, in the sense that there were cities that existed in that um, civilization. It was very developed, and uh, these cities were so organized that there were roads that intersected each other in the perpendicular fashion, as we have streets and avenues in America nowadays. So that idea of perpendicularly intersecting roads existed even in Harappa civilization. The very systematic sanitization and sewage system also existed in that civilization, which showed how uh, well they could think about everything. Those people of that civilization. Uh, Also, these structures that we find in those civilization, in that civilization, are uh, very precise, and that tells us that they could measure everything very well, and that also tells us that their mind had a mathematical bent, because without having a proper mathematical bent of mind, you cannot measure things and you cannot have proper proportions, because even in those constructions, the bricks that are um, found have the ratio of 4 to 2 to 1 uh, for length, width and height, and that is considered as the best ratio for constructions. So they knew it, they must have experimented, and they must have found out this ratio. So even in that civilization, mathematics seemed to be playing an important role. Mathematics also shows in that civilization in mensuration systems, that is the measurements that they have. So they measured weights, they measured lengths. The bronze rulers were found uh, in the at the excavation sites. So it means that they measured the lengths very precisely, the short lengths as well as long lengths, and they also measured weights, because this was a civilization wherein there was a lot of exchange of commodities, there was trade, and therefore naturally they needed weights to measure several objects. So the weights varied um, from as small as 0.05 to as large as 500. So as you can see, the ratio the ratio of the largest weight to the smallest weight is 10,000. So the range, look at the range of this weight. It's a large range. So that tells us how refined their mensuration system was. Also, uh, they had some idea of geometry, because uh, their structures, they had well built houses, they had multi-storied houses as well that were found in the civilization. They had a proper although we cannot say temples, but some unidentified structures that are very well built. They also had a very well built bathing constructions, so that tells us very well built wells as well. So that tells us how they were aware about the geometric constructions, and also some of the um, uh, geometric figures, such as the swastik, as we call it, so swastik nowadays, was found at that site. So even there was some progress in terms of geometry. This is about Harappa civilization. Now let us come to the relatively more recent times. Um, After the it is the Anno Domini, that is AD. So first prominent figure that we stumble upon is Aryabhatta. We have already mentioned about Aryabhatta. Aryabhatta was a mathematician and astronomer. He was born in Patna, at Patliputra, which is now Patna in Bihar, and he studied at the Nalanda University, which was a very renowned university at that time. There were two very renowned universities at that time. One was Nalanda, and the other was Takshashila, which is now in Pakistan. And earlier he studied at Nalanda, and then he also became the head of the university in future. And he is supposed to be the father of Indian mathematics because he is the oldest one and who contributed a lot. It is not true that there were no mathematicians before Aryabhatta, because uh, there are some Sanskrit scriptures or Sanskrit texts available even before Aryabhatta, that are that explain a lot of mathematical formulas, and those mathematical formulas are all compiled in a textbook, and that textbook is called is now known as Shulva Sutras. And Shulva Sutras is a compilation of several mathematical formulas and mathematical principles, and that existed before Aryabhatta. So therefore we cannot call him as the first Indian mathematician, but the first one who contributed a lot. So therefore we call him the father of Indian mathematics. uh, and his contributions are in the pure mathematics as well as in the uh, astronomy. Also, he approximated the value of pi. Here it's written as pi. The importance of the value of pi is in the construction of geometric figures, because pi is the constant which, when multiplied by the diameter of the circle, gives us the circumference of the circle. So it was very necessary for Indian sages or Indians scholars to know the value of pi in order to be able to construct circular Yajna kundas or Havana kundas. And therefore they always tried to find the value of pi as accurately as possible. And you will see in the subsequent slides that some of the successors of Aryabhatta even further uh, they furthered the research on the value of pi, and they gave even better and better approximate values, or better approximated values of pi, that means more accurate values of pi. um, there is yet another achievement by Aryabhatta which is not written over here. Aryabhatta also, with his knowledge of astronomy and the motion of the stars and planets, gave the diameter, tried to estimate the diameter of the earth, and very surprisingly the error in his estimation is only 1%. Now we know the exact diameter of the earth using the modern equipments, the satellites, etc. So now we can calculate the diameter of the earth almost perfectly, and the diameter of the earth that he calculated, uh, varies, that has only 1% error in comparison to the actual diameter of the earth, and that is an astounding discovery in my opinion. uh, there are two main books that are written by Aryabhatta. One is Aryabhatta Siddhanta, or Arya Siddhanta in short, that is called, and second is Aryabhatiya. Aryabhatiya mainly deals with mathematics, whereas Arya Siddhanta mainly deals with astronomy. In Aryabhatiya, he develops several mathematical theories that are used for astronomy. For example, the table of sine. So sine is a trigonometric ratio that is used for that is used in geometry and also in astronomy, and it's a very important ratio. And the more accurate value of uh, the more accurate sine values you know, the better are the better calculations you can do, and the better results we can obtain. So he is known for known for having given sine values for 24 different angles to a good accuracy level, which was very difficult at that time. Um, so these are the contributions of Aryabhatta in short. So he um, introduced alphabetical counting system. He was the first one to calculate these square roots and cube roots of certain numbers. So it's not that easy to calculate square root and cube root of even some of these uh, small integers. For example, the value of square root of 2 is not easy to calculate using basic techniques, but he did it. He gave solutions to equations like these: by equal to ax plus c and by equal to ax minus c. These are called as linear Pales equations that were studied in Europe quite late, uh, as late as in the 17th century. But these were studied by Aryabhatta quite as early as in the 7th century. He provided the approximate value of pi, the importance of which we have already discussed. He was the one who said that pi is an irrational number. So irrational number is a number which cannot be expressed as a ratio of two integers. And he, although did not prove uh, that pi is an irrational number, he conjectured that pi could be an irrational number, and he had a fair idea about this fact. Afterward, in the 18th century, it was proved that pi is an irrational number by a European mathematician. And not only Aryabhatta, but even far before Aryabhatta, as I said, in Shulva Sutras, the existence of irrational numbers has been implicitly mentioned, in the sense that they could not prove that certain numbers were irrational, but they had an idea that probably square root of 2 is an irrational number, which is a fact. It was proved uh, uh, by ancient Greek mathematicians, by one of by an ancient Greek mathematician, that square root of 2 is an irrational number. But before that, Indians knew, they had surmised that square root of 2 must be an irrational number. It could not be expressed as the ratio of two integers. So the existence of irrational numbers, where um, they could ideate this concept of irrational numbers. He formulated the tables of sines, and also he gave the sum of the first n integers, the formula for sum of n integers, which is not that easy. Alright, some other facts about Aryabhatta. The Hindu calendar that we use, that is lunar calendar. In Hindu calendar we have months that change according to the cycle, the moon cycle, and the uh, the year is based on um, the revolution of Earth around the Sun, and to coordinate the two things together is a major challenge that was handled by Aryabhatta. And there is a confusion in his name. There are, yes, there are some people say that there are two different Aryabhattas, and also it is not known uh, which work belongs to which Aryabhatta, but uh, it is irrelevant. What is important is that there was a mathematician who contributed and who discovered so many things. Aryabhatta set up an observatory uh, at a place called Taravana, and as we have already mentioned, he served as the head of Nalanda University uh, in his in his last days. I mean, when he became a senior mathematician, he was appointed as the head of Nalanda University. Now comes Brahmagupta, who was a successor of Aryabhatta. Um, Brahmagupta was born in Billamala, which is now called Bhinmal. He was born in 598 AD. Even he worked in astronomy as well as in mathematics, and he was an astronomer of Brahma Paksha school. So there are different thought schools. There were the different thought schools at that time in India. One was Pitamaha Paksha school. One was the Pitamaha Paksha school. In fact, Brahma Gupta was a student of Pitamaha Paksha school, but since he made several contributions to that thought school and made several corrections in that school, thought school, later on it came to be known as Brahma Paksha school. Also, there was another thought school that is called Arya Paksha school. That was Aryabhatta, that was named after Aryabhatta. So the students of Aryabhatta mainly followed those principles, and there is also another school called Surya Paksha. So these are different thought schools, and the main difference between them is that their method of measuring time was little different, but the conclusions that they uh, obtained after, I mean, as a result, were almost the same. So therefore, there is practically not much difference between them. It's just that it's just a matter of it's an academic interest. So therefore, we shall not discuss that in greater detail. Uh, he studied the works of his predecessors, Aryabhatta, Sri Sena, and as you can see over here, Vijayanandin Latadeva, Pradyumna, Simha, Varaha Mihira. Varaha Mihira is a mathematician about whom we shall discuss in detail in the subsequent slides. Um, uh, when he was 30 years old, he wrote the text called Brahma Sputa Siddhanta, which was a revised version of Siddhantas, which he studied in Brahmapaksha school. So, as I said, the Brahmapaksha school was earlier called as Pitamaha Paksha, and since he uh, made some contributions, he added a lot. Uh, Added a lot of new things to this book, and he corrected some of the principles. This Pitamaha Paksha school afterwards came to be known as Brahma Paksha school, and the new text that he wrote then came to be known as Brahma Sputa Siddhanta. He then afterwards he moved to Ujjain. Ujjain is at that time was one of the best places to study astronomy. There was a congregation of several good astronomers and mathematicians at that place. Um, at the age of 67, he wrote Khanda Khadyaka for his students. Khanda Khadyaka literally means an edible bite of food. That means something that you can at a time eat and easily digest. So he probably knew that some of the students cannot digest too much at a time. So therefore, he uh, collected some of the easier topics in uh, in the field of astronomy. Uh, Collected them, wrote it in a book, and this book Khanda Khadyaka is divided in 12 parts, 12 adhyayas as he called them, and each adhyaya or each part, each section discusses some of the basic things in astronomy, such as um, the waxing and waning of moon, and then also the conjunction of two stars and eclipses and so on. So this is about um, Brahmagupta. Then comes uh, Bhaskaracharya 1. There are two Bhaskaracharyas in India. The first one was in the 7th century, and the main contribution of this Bhaskaracharya was to take ahead the works of Aryabhatta. He was a student of Aryabhatta's astronomical school, and he refined the works of Aryabhatta. So he worked on the sine function and gave a better approximations of sine functions. And also he uh, gave a better approximation for the value of pi, as we said that the working on the value of pi and giving more and more precise value of pi was one of the main tasks before the mathematicians of that time. And first Bhaskaracharya contributed to that as well. He wrote 3 books. One was Aryabhattiya Bhashya, which is a commentary on the contributions of Aryabhatta. He tried to simplify the principles that were laid down by Aryabhatta. Then there is Laghu Bhaskariya, and then there is Mahabhaskariya. The Laghu Bhaskariya is the small book by Bhaskara, and Mahabhaskariya is the great book by Bhaskara. And this in Mahabhaskariya, as it is a great book, there are 8 chapters, and there is a detailed discussion about the astronomical phenomena in this book. The contributions of first Bhaskaracharya in mathematics. He worked with the number 0. So as you will see, the students of Aryabhatta and the successor of Aryabhatta were more interested in researching in the fields where Aryabhatta already had researched. So decimal systems, the number 0, the value of pi, the then the also some of others, the sine function or the value of these sine functions, I mean sine of x for various values of x, and getting better and better values of the sine of x, etc. So these successors of Aryabhatta took further this research that was already done by Aryabhatta, and Bhaskaracharya was one of them. So um, these are the achievements of first Bhaskaracharya. And ISRO, that is the Indian Space Research Organization, launched the satellite which was named after Bhaskaracharya on 7th of July 1979. Next comes Varaha Mihir in chronological order. Varaha Mihir was a mathematician who was born and brought up in Ujjain, which is now in Madhya Pradesh. Varaha Mihira was not only a mathematician but also he was not only a mathematician and astronomer but also was an astrologer. So there is a difference between astronomy and astrology, as some of you might know. Astronomy deals with the study of motion of the celestial bodies and the calculations with their positions, whereas astrology believes that these celestial bodies have some effect on human life and tries to connect the two and tries to also predict some of the events in the human life based on the positions of the stars and planets in the space. And he was Varaha Mihira was not only an astronomer but also an astrologer, and he was one of the 9 jewels, Navaratnas, in the court of the emperor Yashodharman Vikramaditya of Malwa. Malwa is a region in Madhya Pradesh nowadays. So again, Madhya Pradesh shows up. He was brought up in Ujjain, studied in Ujjain, and then he was appointed in the court of Vikramaditya. And some mathematicians believe that he had strong knowledge of predictive calculations and zodiac signs. So here again astrology shows up, his knowledge of astrology, and he used to perform astrological computations and auspicious ceremonies in India in those days. So again auspicious ceremonies means yajnas, etc. And also some of the auspicious ceremonies include marriages or some other samskaras that are held in the householders' families. So to conduct these ceremonies, some of the best times are chosen that we call muhurtas, and those muhurtas are based on the positions of stars and planets, and for that you need to know, you have to have knowledge of astronomy, and Varaha Mihir was an authority on that, and therefore he was highly respected in this manner, in this regard, at that time in India. Varahamir wrote um, uh, two books. One is Pancha Siddhantika, and the other is Brihad Samhita. Brihad Samhita is a very large book, which is Brihat Samhita itself. Samhita means compilation, and Brihat means large, or rather very large. And so that it literally means great compilation, and it has 106 chapters. And this book not only contains the discussions on uh, just maths and astronomy, but everything that in which mathemat- mathematics is attached to. There, that means architecture, mathematics, gemology. Gemology is the study of gems. Then design of temples, planetary motions, and astrology, cloud formation, as you can see over here. So everything um, uh, that has something to do with mathematics basically. And therefore many things come into this, uh, and therefore the book becomes very large, and therefore it is called Brihat Samhita. And the first one is Pancha Siddhantika, which is about mathematical astronomy, and this is basically uh, the um, a commentary on the five essays, or five um, treatises, or five texts that were written earlier, uh, namely Paulus Siddhanta, Pitamaha Siddhanta, about which we have already said something, Surya Siddhanta, Vasishtha Siddhanta, and Romaka Siddhanta. Pitamaha Siddhanta is something that was corrected afterward by Brahmagupta, and then Pitamaha, the people who followed Pitamaha Siddhanta were called as the people of Pitamaha Paksha, which then came to be known as Brahma Paksha, as we said earlier. The people of Surya Siddhanta were called as the people of Surya Paksha. He commented on each of these, and that scripture is now called as Pancha Siddhantika. So these were the contributions of Varaha Mihir. Then Varaha Mihir also created sine tables. As we said, again sine comes in over here, because the sine values are very important again in geometric constructions as well as in the study of astronomy. Uh, and as we saw, sine tables were created by Aryabhatta but were improved by Varahamihir. Again here you can see that the successors of Aryabhatta are taking ahead the researches of Aryabhatta. Uh, he discovered a version of Pascal's triangle. So a Pascal triangle is named after a European mathematician Pascal, but it was known to Indian mathematician earlier. Pascal triangle is a triangle uh, which is for example, it's a triangle having n rows, so n can be any positive integer. You can write it to any value n, for any value n, and if you write it for a certain value of n, then every nth row contains n numbers in a horizontally written, and the first and the last entry of every row is 1. So the first row will contain only one number, that is 1. The second row will contain two numbers, 1 and 1. The first and last number is 1, so there are only two numbers, so both numbers will be 1. The third row will contain three numbers, fourth row will contain four numbers, and so on. And every row has 1 as the first and the last entry, and in every the two successive entries of every row are added, and the sum is written uh, in the next row, in between, in the midway between the uh, those two entries, and in that way you create or you form Pascal triangle, you construct Pascal's triangle, and the numbers in this Pascal triangle are binomial coefficients, as mathematics students may know. In fact, Varahamihir also was aware of binomial coefficients, which were found in Europe much later. Also, Varahamihir constructed 4 by 4 magic square. Um, Magic square, 4 by 4 magic square is a square in which there are 4 rows and 4 columns, and therefore 16 cells, and the numbers 1 to 16 are placed in those 16 cells in such a way that the numbers in each row, in each column, and on the diagonals add up to the same number. So the sum of the numbers in each row, each column, and the sum also on the two diagonals is the same. And he constructed this magic square. He was the first one to talk about Ayanamsha or Ayanabhaga. Ayanamsha and Ayanabhaga are is a very complex thing in astronomy. There is apart from two motions of the earth that we generally know, which is the revolution of the earth around itself and the revolution of the earth around the sun, there are some more motions that the earth is going through, and that affects the equinoxes, and that also affects the season cycle. But that is those that motion of the earth is so subtle that it is very difficult to detect for a person in his small lifespan. The lifespan of a person is around 100 years, or I mean at most 100 years or above, not more than that. It's very difficult to observe changes during this period when the motion is so subtle, but he could detect the some of the changes. He could observe some of the changes and propound some theories, and he could therefore tell for certain that there are some motions of the earth apart from the revolution about itself and revolution about around the sun. And now some interesting facts about Varahamihir. He was an astrologer, as we have seen. He could predict many things based on the positions of stars, sun and moon and planets. He has constructed Meru Stambha, which is also again used for astronomical purposes. He proposed that planets and moons they shine because of sunlight, and they do not have their own light. This is again something very striking, because in the space, planets and the stars look alike. Both are emanating light. So therefore you do not know a priori, I mean there is no way to know whether the an object is emitting light of its own, or it is only reflecting a light that is coming from some other source. But in some way he could propose it. He is the person who said that earth was spherical. In fact, it is believed that Indians knew that the celestial bodies were spherical, because the name for astronomy in Sanskrit words Khagola Shastra. Shastra means science, Gol means sphere, and Kha means space. So it is the science of the spherical bodies in this space. So that means they probably knew that these objects, these objects in the space are spherical. Also, the um, the science of Earth is called Bhugol Shastra, which means Bhu means the Earth and Gol means the sphere, and therefore it also is possible that they knew that the Earth is spherical, which is written over here. And he also wrote the Jyotish Shastra, which is Jyotish astrology, which is nowadays called as Phala Jyotisha. Now comes the next chapter, that is Bhaskaracharya second. Bhaskaracharya second is his main contributions are in algebra, and one thing about Bhaskaracharya to know for at least those who are Maharashtrian students, Marathi students, is that he was born in Maharashtra, near Patan, near Chalisgaon or Jalgaon. He is arguably the first Indian mathematicians to use algebraic methods to solve mathematical problems so profusely. Uh, Not that algebra was completely unknown to mathematicians before Bhaskaracharya II, but he took algebra to another level, and therefore he is believed to be the father of algebra in India at least. His most notable work is Siddhanta Shiromani, which is divided into three major parts. The first is called Lilavati, which deals with arithmetic, and this part is named after his daughter Lilavati. And it is also believed that Lilavati, who became widow very soon after her marriage and came home, and he taught her mathematics to amuse her, or to distract, to just to take away her grief and pain, and therefore he taught her mathematics, and then that he was compiled, and that then was changed into converted into a textbook, became Lilavati. And the second part is Bijaganit, which is algebra, and the third part is Graha Ganit, which deals with astronomy. And the one of the peculiarities of this scripture is that the problem statements are so poetic in nature, that that if you read that book, then you really will not feel that mathematics is a dry subject. Very that is quite in contrast with general perception that mathematical language is very dry. Now, some of the most important contributions by Bhaskaracharya, and that is something that we must always remember. These contributions are really remarkable and deserve attention by everybody, especially by the students of mathematics, because the methods that he developed for solving some of the intricate problems were developed in Europe far later, in 18th or 19th century. So he developed methods for solving what is nowadays called indeterminate equations, that he called Kuttaka, that were studied in Europe much later. He invented a method called Chakraval for solving a class of problems called Pell's equation. We earlier have seen that Pell's equations also were solved by Aryabhatta, but those were linear Pales equations. The Pales equations is a class of problems which were also solved by Bhaskaracharya. But these Pales equations are even more complicated. These are called quadratic Pales equations. Uh, and this method Chakrawala was independently invented in Europe in the 18th century by another great mathematician, Euler. Uh, Calculus was invented and was fully developed by Sir Isaac Newton in the 17th century, but Bhaskaracharya already had thought about the foundational ideas of calculus. He uh, talked about the ratio of two infinitesimally small quantities, and that is nothing but the foundational idea of calculus. But unfortunately he couldn't take this idea to completion. Somewhere he blundered and his calculations went wrong, and nobody afterwards took those ideas ahead. This flow of thoughts was disrupted. Uh, and then independently those ideas were afterwards invented and developed by Isaac Newton in Europe, in England. Although he could not develop the theory of calculus, he could appreciate the importance of the idea of rate of change, which is called as the derivative of a function in these days, modern days. And very cleverly, he observed that sine function changes like cosine function, and cosine function changes like negative of the sine of the function. So as we call it in the mathematical terminology, derivative of sine is cosine and derivative of cosine is the negative of sine. But he had already observed this, although uh, he could not express it mathematically. The Pythagoras theorem was known to ancient Indians, and they used it uh, very much from time to time for constructions, geometric constructions, for like Yagnakundas, etc. But nobody actually proved the why the theorem is called as Pythagoras theorem is because Pythagoras was the first one to give a theoretical proof of that theorem. Again, here there is some debate about whether Pythagoras was the first one to prove it or not, because this theorem also was known to Chinese people, and one ancient Chinese mathematician called Gogu also has given a theoretical proof of this theorem. Now it is difficult to tell whether Pythagoras was the first one or Gogu was the first one to prove this theorem. But Bhaskaracharya was the first Indian to give the proof of his own. Of course, Bhaskaracharya comes uh, is relatively much modern, and he was born much after Pythagoras, and therefore the theorem cannot be ascribed to him. But he gave his own proof. Bhaskaracharya afterwards was appointed as the head of the observatory at Ujjain, where he remained till his last days. That is about Bhaskaracharya. Then comes Madhava of Sangamagram. Sangamagram is a village or a town in Kerala of these days, and he was again another great mathematician. Um, Majority of his books, he was a prolific writer and a very good teacher. But most of his work has been now lost. But some books were found and retrieved, and that those books tell us quite a lot about his researches. Again, these are some of the books that he wrote. Aganita Grahakara, Chandra Vakyani, Gola Vada, लग्न प्रकरण, देन माध्यम नयन प्रकार, देन महाजन्य नयन प्रकार, महाजनयन प्रकार, स्फुटचंद्रापति, वेनवरोह. These are some of the important books that are written by him. And one of the main things about Madhava, where what distinguishes Madhava from the previous mathematicians, is that he is the father of considered as the founder of mathematical analysis in India. He was one of those, or rather probably the first one, who could understand that the sum of infinitely many numbers can be a finite number. This idea may not be may not be familiar to these to those who are not familiar to mathematics. I mean, those who haven't studied mathematics, but those who have studied some mathematics will know uh, this fact, that sum of infinitely many numbers can be finite. And it is not easy to conceive this idea, but Madhava observed this, and he not only observed this, but he used this. He not only sort of added infinitely many numbers and showed that the sum of those infinitely many numbers can be finite, but also he extended that idea to functions, and he wrote power series for certain functions such as sine of x and cosine of x, and also logarithm functions. So he using those ideas of the series of functions, he could find better and better approximations of these sine values and cosine values of certain numbers. So that actually is a big achievement of Madhava. So polynomials are the functions which were known to Indians before, but power series are the extension of polynomials to infinity, and that is what he could conceptualize and actually put it to use. That is one of the important contribution here. He also derived infinite series summation formula for pi. Again here we can see that finding better and better value of pi is important here, and for Indians it was certainly important, and he gave an infinite series for pi, which resulted into a better value of pi. Now some interesting facts about Madhava. Madhava is the most significant medieval India's mathematician and astronomer. He is the founder of mathematical analysis. This idea of in taking the sum of infinitely many numbers and still getting a finite number is typical to analysis. That is what is you can say lies at the core of something called as analysis, and therefore he is called as the founder of mathematical analysis in India. A similar work was done in Europe by a mathematician called Weierstrass, and therefore in Europe Weierstrass is called as the founder of mathematical analysis. He is the founder of the most famous school called Kerala School of Astronomy and Mathematics. he derived the trigonometric tables because he could work with sine and cosine functions like nobody else, and therefore naturally he could easily uh, create trigonometrical tables. Uh, and there are some awards given in the name of Madhava. Uh, Madhava award is given to undergraduate students. So Indian government, rather National Board for Higher Mathematics, has uh, began this award uh, for undergraduate students, and this is a prize given to students by Homi Bhabha Center for Science Education and the Department of Mathematics of SP College Pune, Sir Parshuram College Pune, and that is about Madhava. And Madhava Mathematics Academy has been founded in Pune, Maharashtra. Now we are coming toward the end of this presentation. Uh, we have discussed quite a lot about the ancient Indian mathematicians and their contributions, so to say. Now we are coming toward more modern times. Although it is the objective of this presentation was to discuss the mathematics in ancient India, uh, it will not be proper to finish this presentation without the mention of some of the prominent figures in modern mathematics. It will be incomplete. So the most legendary mathematician of the recent times, and he is probably the one of the greatest mathematicians of all times, is Srinivas Ramanujan, who was born in Tamil Nadu. He was a child prodigy in the sense that he was as if he was born with the knowledge of mathematics, natural bent of mathematics, natural bent of mind for mathematics, and in this short presentation, it is impossible to discuss about his achievements and his contributions, but we shall quickly go through some of the salient contributions. Initially, he did not receive any formal training in mathematics in his childhood until he went to high school. Uh, but by the time he went to high school, he was a self-taught mathematician initially. Uh, he borrowed some of the books from his senior students, and he taught himself trigonometry from some of the very famous books at that time, the books that were written by some of the famous mathematicians called Lone, etc. He also had started solving algebraic equations, quadratic equations. He also solved cubic equations. He also solved quartic equations, which is very difficult. And also he attempted solving quintic equations, which is the equation of the fifth degree equation. But he did not know at that time that it is impossible to solve the fifth degree equation. It is proved. It was proved by a French mathematician earlier that it is impossible to solve an equation of the fifth degree general equation. Uh, Afterwards, recognizing his talent, he was given scholarship by Madras University to pursue his studies in mathematics, and then he corresponded with some of the eminent mathematicians, British mathematicians of that time, and they invited him to England to uh, to continue his research in England. So he traveled to England at the time. His main work is in the field of infinite series, arithmetic functions, and partial fractions, and many other tau functions for that matter. Um, he is arguably the mathematician, the who dealt with the idea of infinity the best. Nobody dealt with the idea of infinity as good as he did. Uh, in Hollywood, they have produced a movie on the life of Ramanujan, whose title is "The Man Who Knew Infinity," which is, I think, available on YouTube. And some of you, those who are interested, can watch that movie. Um, it is said that Ramanujan's ideas were completely intuition driven. Even he admitted that his intuition drove him to those ideas. They were not, he did not actually work out those ideas by like following any logic, though he believed that his family goddess Namagiri showed him those formulas. Sometimes he also saw those formulas during his when he was sleeping, and he just jotted down those formulas or those mathematical results, and he proved them afterwards. So proofs came later. He was inspired to to those formulas, and uh, therefore to many people at that time, uh, his formulas and his mathematical results seemed completely inscrutable. uh, and But every time his formulas and his mathematical results turned out to be correct, although he did not they came like they seemed to be coming out of nothing. They turned out to be true, and afterwards he used to provide proofs for those mathematical results. Just to uh, give a glimpse of how the genius of Ramanujan, uh, here is given in green color the very celebrated infinite series that he gave to approximate the value of pi. This series is known to have the fastest rate of convergence. That means even if you take, see, this series extends to infinity. Again, for those who study mathematics, might know that you can take infinite sum, and that infinite sum can have finite value. Here, even if you take the first term of this infinite series, the value that you get of pi is correct up to 6 decimal places after a decimal point. So that tells us how correct this formula is, or how precise value of pi this formula gives us. That is about Raman. There is a lot that can be said about Ramanujan, but due to the since the time is running short, we shall skip that. Now we shall come to the last mathematician that we want to discuss today. That is Dattatreya Kaprekar, and we have included it in this presentation because Kaprekar was a resident of Nashik. Although he was born in at Dahanu, he he studied at Ferguson College, Pune, and then moved to Nashik, and he taught. Uh, uh, he worked as a uh, school teacher in Nashik, uh, and he resided in Nashik till the end. Uh, he loved to sit at the banks of Godavari or at his home in solitude and play with numbers and examine their properties. So he is, so to say, a recreational mathematician, very often, as he is called. So he did not. He was not, so to say, a proper university professor or someone who worked at the higher level mathematics, but he played with numbers and examined the properties of numbers and experimented a lot with them. But some very amazing results came out of that, which were afterwards taken cognizance of, and some mathematicians afterwards studied those results, and um, then they proved certain theorems that were related to those results. Uh, some of the astounding discoveries by Kaprekar were uh, the numbers 6174 and 495, which are called Kaprekar constants, and also some numbers that are called Harshad numbers. Uh, Harshada numbers, this the word Harshada comes from, he actually called them Harshada because they are joy givers. Harshada means the thing that gives you joy, and since he found a lot of joy while uh, experimenting and playing with these numbers, he called them Harshada numbers. You can read about Harshada numbers on internet. It is not the proper place to discuss these numbers because the idea is somewhat complicated. But let us discuss what Koprekar constants are. Uh, Let us take this number. These two are the only numbers that are Koprekar constants. There are no other Koprekar constants. So, what is a Kaprekar constant? Let's take this 495 and see what the property this 495 possesses. So, to see, consider any three-digit number. Begin with any three-digit number. Let's say 934. The only condition that a three-digit number satisfies is that it should not have all three digits the same. Okay, there should be at least two digits that are different from each other. Here we have taken all three digits different. Now make uh, uh, two numbers out using the digits in this given number that we started with. That one number that is the largest and the other smallest. So here we have done it. 943 is the largest number that can be produced out of this given number 934, and the smallest number is 349. Now take the difference between the two numbers, that subtract, you get 594. Now repeat the same process for 594. That means again form the largest number using the digits and form the smallest number. Here the largest number is 954 and the smallest number is 459. Again take the difference, subtract this, we get 495. Now repeat the process with this 495. Take the largest number, that is 954, and the smallest number is 459, and take the difference, you get the same number again, 495. And now that 495, after carrying out this process, gives us 495 again. This will repeat, and this number 495 will keep repeating, so that this process stabilizes here at this number 495, and therefore this is called this number is called Kaprekar constant, and this holds for any three-digit number. You start from any three-digit number. Here we have started from 934. Instead, you can experiment yourself. You can start with any number, and you will realize that you arrive at this number 495 at the end, and this is called as the Kaprekar constant. And similarly, if you try out any four-digit number and carry out the same process, then you reach this number 6174, and the same number keeps repeating eventually. So these two numbers are called Kaprekar constants. So with this we wind up our lecture. This is the final part, the the uses of mathematics in medicines. Um, so it is very often believed that uh, mathematics is has is not used in the medical science, but that is not true. Very often, in at least in India, biology students take up medicine and mathematics students take up engineering. But this slide is created in order to emphasize that there are a lot of uses of mathematics in medicine as well. For example, these X-rays and CT scans and MRIs, they are all basically they are all images, and this is through image processing that we can get these images. And there is a, an altogether different subject in mathematics called linear algebra that is used for image processing. And there is a lot of use of mathematics in pharmacology. In fact, pharmacology students have one paper in mathematics. In fact, even the entrance exam for pharmacology has a mathematics section. So that is something that you should take into account. um, the, the Nowadays a lot of data is collected, patients data is collected, and for diagnosis the data is processed, and data science techniques are used in um, medicine. For the use of data science also depends on mathematics to a large extent, and this data science uh, helps us to uh, predict the a lot of things about patients and the outcomes. Also, uh, there are some other uh, uses of mathematics in um, medicines, such as comparing brains. So that means again here comes in the comparison of two images. So here again image processing shows up. So in fact, just to on a lighter note, I would like to add that in India it is compulsory to have biology as one of your subjects in the 12th standard to take up medical field. But in Europe and America, to the best of my belief and to the best of my knowledge, even if you do not have biology as a subject but you have mathematics, if you have studied mathematics at the 12th level, then you can opt for medicine. uh, because mathematics is foundational to majority of the subjects that we study. um, all right, so with this we end our lecture. If you want to read something more about all that we have already gone through, then you can visit this website Vedic Math School, and there you can read uh, good about many more things about mathematics of in the ancient times as well as modern times. So thank you very much for listening to this lecture, and all the best for your future. Thank you very much.